Rates of change. Okay, so we've learned about two kinds of rates of change, the average rate of change and the instantaneous rate of change. The average rate of change is the change in the y compared to the change in x, or with function notation, the change between the two y values compared to the change in those two x values. The instantaneous rate of change we now know as the derivative at a certain point, and we can define that as the limit as x approaches 0 of the change, or the limit as one x value approaches another x value with the difference quotient. Let's see how we can start to use this. Imagine that you have a circle and you want to know how fast is the area changing as you increase the radius. Well, we can use some of the calculus that we now know to answer that question. So we know the area of a circle is pi r squared, and we'll take a look and see how fast the area is changing when the radius is 4. And what we need to calculate is the change in area as the radius changes. So area prime with respect to r is 2 pi r, taking the derivative of pi r squared, and at a radius of 4 it is changing 8 pi, and what that means is you're adding in an additional area to the outside at this rate when r is 4. As our x values become really close with any secant line, as they become closer and closer and closer together, we're estimating the tangent better and better and better. And so it's also true that for really small values of h, the difference quotient is really close to the derivative, or the derivative is really close, approximates the difference between a couple of that the derivative is approximately the same as that tangent slope. And it turns out that if we change the h by just 1 unit, so if that h value is just 1, then this formula becomes something quite easy to work with. And you can see that now we can estimate the derivative by finding two consecutive values on our graph. This can be really useful when we are trying to approximate how much something changes at a certain rate. This can be really useful when we're wondering by approximately how much something changes at a certain value. Let's take a look at an example of this. For an airline to operate a flight, say Vancouver to Seattle, it costs, and the cost function is modeled by this equation, and x is the number of passengers. So part A is estimate the additional, also known as the marginal cost, add one more passenger if the flight already has 200 passengers. So to do this, we can estimate it by using the derivative, and the derivative of this is shown with this function. And so with 200 passengers, it costs approximately $28 to add an additional person. You can verify that with your graphing calculator. Part B. What's the actual cost difference? Well, however much it costs us to put the 202nd person on the flight, minus however much it costs to put 200 people on the flight, and that turns out to be approximately, well, $28 approximately, but $27.92 exactly. Our next example is a child's rocket is shot with an initial velocity of 60 meters per second at an initial height of 40 meters, and we want to find the maximum height. To do this, we need to use Galileo's formulas, the height formula, and the velocity formula. Notice that the velocity formula is the first derivative with respect to time of the height formula. And on Earth, g is approximately 9.8 meters per second. SO and VO are the initial conditions or initial values for initial height and initial velocity. So when this rocket gets fired up, when the velocity becomes 0, it's going to hit its maximum, then it's going to start falling back down to Earth. So the first thing that we want to do is figure out at what time does that velocity equal 0. So let's set up the equation. And we know our original velocity is 60 meters per second, gravity is 9.8, and we want the velocity to become 0. Solving for t gives us a value of approximately 6.12 seconds. We can then use that in our position formula, and our position formula has an initial height of 40 meters, an initial velocity of 60, with that time, 6.12 minus 1/2 gravity times the time squared. And if you calculate this, our rocket gets to a maximum height of approximately 223.7 meters.